Okay, this is the first part of lecture 22 on the kinematics for cosmology. So in this lecture, which is basically section 8.2 in the book, we talk about homogeneous isotropic universe. Um, the kinematics for GR is leads to us to say the space-time described by the Robertson-Walker metric when this is done in the co-moving coordinates. And we see once this kinematic set up, the Hubble's law of expanding universe follows automatically. Most modern cosmology start with something, a working hypothesis called the cosmological principle, which states that each epoch, each time, the universe is homogeneous isotropic in space. Okay. It presents the same aspect except for local irregularities at each point. The universe has no center, no edge. The absence of any privileged location is, in some sense, is a fundamental generalization of the Copernican principle. And this the assumption of homogeneous isotropic space has been confirmed by modern astronomical observations, especially by the cosmic background radiation, which is in every direction is homogeneous to 1 part in 100,000. Now, but we have the irregularity. So the observed irregularity, for example, we say the structure universe, the stars and galaxies and clusters of galaxies, voids, these are assumed to have arisen from gravitational clumping around some initial density unevenness. Okay. It was somehow at the beginning, there's some unevenness in the density, some fluctuations. And then gravity always tends to enhance this unevenness by clumping together. So, so the question of what mechanism we can generate this density perturbation to begin with, and we basically will talk about the quantum fluctuations in the earliest moment of the universe, when those quantum fluctuations are inflated to astronomical sizes, thereby establish the initial lumpiness required for the formation of observed cosmic structure. So basically, we're assuming the homogeneous isotropic space, but on the side, we assume there's some sort of density perturbation that will generate the initial density unevenness, which eventually will uh, form the seeds of structures in the universe. The cosmic picture implied by the cosmological principle is that the universe filled with cosmic fluid. The fundamental particle of these fluids are the galaxies. Each fluid element has a volume that contains many galaxies, yet is small compared to the whole universe. Just like we normally describe a fluid like water, it's a fluid and it's made of atoms and molecules, and each fluid element contains many atoms, many molecules, but each fluid element is still small compared to the fluid as a whole. So therefore, the motion of cosmic fluid element is average or smeared out motion of the constituent galaxies. This motion reflects their mutual gravitational interaction. So in other words, each fluid elements are in free fall, falling geodesics. And in reality, this cosmological uh, picture that the random motion is rather small is confirmed by observation. Is the relative random motion is only about 1 part in 1,000. Now we can say something about the co-moving coordinates. This cosmic picture allows us to pick a privileged coordinate frame. This is so-called the co-moving frame, in which the coordinate time is taken to the proper time of each fluid element, and the spatial coordinate xi is carried by each fluid element. Okay. So therefore, a co-moving observer flows, follows a free fall in the cosmic fluid elements, and this this free fall, this motion is called the Hubble flow, because each fluid element carries its own fixed position labels. The co-moving coordinates really can be regarded as the rest frame of the cosmos, rest coordinate frame of the cosmos. And the metric described in space-time is called the Robertson-Walker metric. It's in this co-moving frame. The coordinate time being the proper time of fluid element, so that the 0, 0 component of the metric is -1, just like in the uh, in the in the in the in the, in the in the gravity-free metric. And it's because we can talk about space for a given time, so therefore the space like slices for fixed t can be defined. So it means that the spatial axis and the time axis must be orthogonal, which means the spatial, there's no cross term in the metric. So the GI0, G0I are 0. So the four-dimensional space-time metric satisfy the cosmological principle is a block diagonal 4x4 matrix, okay, in the co-moving coordinates, in which you have this row of zeros, this column of zeros, and only diagonal element. But of course, this part is 3x3 matrix, describe the spatial part of the metric, in which the G00 is -1, and these uh, 0 columns, 0 rows, and then a 3x3 spatial metric. So right in terms of invariant interval is of course minus c squared t squared plus gij dxi dxj, and this part we call dl squared. Now the cosmological principle, which says no preferred direction or position in the 3D space, so therefore the time dependence of the gij must be an overall factor, overall scale factor, let's call A, with no dependence on any spatial coordinates. It was all the time dependence in this overall factor. dl0 equal to a squared dl tilde square. So dl tilde, of course, is time independent. The scale factor A is normalized at the present epoch to be 1. So it was when t equal t naught, the A is equal to 1. So the fixed, the co-moving length element L tilde is represent the present proper length. So the picture you have is like a 3D map, okay, which causes the cosmic fluid element labeled by some fixed, which means time independent coordinate course x tilde, okay, and the time evolution, the time dependence enters entirely through the time dependence of the map scale. Like any map, right? You have a scale on the side. Let's say 1 megaparsec represented by 1 inch, and then but the time dependence all in the scale. So uh, I don't know, 5 billion years later, 1 parsec is represented by half an inch, so on and so forth. As the universe expands, which means A increases, the relative distance relations are not changed. The relative, the shape of things are not changed. The relative distance relations are not changed. Now, the cosmological principle of 3D space is homogeneous isotropic. So one naturally expect this kind of space to for a given time to have the same curvature everywhere. Okay. So this should be a space with constant curvature. Now we already talked about space with constant curvature in lecture 12. We start first talking about 2D space with constant curvature. Then we say all you basically do is replacing the azimuth angle by the solid angle. You can get to 3D space. 3D space with constant curvature. Here's an example of for the cylindrical coordinates, and dl squared would be some overall length scale, and this this omega is the solid angle, and psi rho over some fixed lengths r naught is cylindrical radial coordinates. Now, this parameter k here is called the signature curvature signature. Can have value +1, -1, or 0. For k equal +1, we're talking about positive curves 3D space. Is we say that we have a closed universe. Okay. For k equal to -1, we have a negative curved 3D space or 3 pseudosphere. We call this universe is open universe. K equals 0 is a flat universe for flat 3D space. In GR theory, the mass energy content of the universe determines, for example, the density parameter omega, which is density over critical density, determines the geometric form, which determines the scale factor A and the curvature signature K. Okay, now, this omega here is solid angle. This omega here is the density parameter. Okay. So therefore, for example, we draw 2D cartoons of this 3D space, a 3D 3 sphere represented by this two spherical surface. So therefore, for omega greater than when the density is greater than critical density, we have a positive curved 3 sphere, and for density less than critical density, we have a negative. We have a 3D pseudosphere represented by here, saddle surface for the 2D cartoon, and for flat space when it's the density exactly equal to critical density. So let's summarize the Robertson-Walker metric. You have the time component just like a G0 minus 1, so it's just simple minus c squared dt squared, and then the scale, the length square, and the dimensionless factor here. And this, the point, of course, this metric is compatible with the cosmological principle, the homogeneous isotropic space. Okay, that's a mathematical fact. There are two unknown factors, the scale factor A and the curvature signature K. Okay. And psi, the time independent dimensionless radial coordinates, with R not being some fixed length. So to give you an example, what's meant by a fixed length? For example, in the case k equals +1 universe, when it's a closed universe, R naught simply is the present radius of the 3 sphere, the S3, okay, whose size, of course, changes with A. So, for example, we'll consider S3, the 3 sphere embedded in a 2D Euclidean space. It would be written as like a W squared in WXYZ of this embedding space coordinates, x squared plus y squared z squared equal to a squared. So when a equal to 1, that's just the radius r naught. So that's the end of the first part of lecture 22.